Assalamualaikum everyone. Okay, so in previous session we discussed like how we can design Google Drive, like how we can design cloud storage service like Google Drive, Dropbox, OneDrive, or Apple iCloud, and we discussed the high-level design deep dive, and all those kind of things. Today we will discuss the proximity service. So, what is a proximity service? It is a service that is used to discover the nearby places. These can be restaurants like businesses, these can be restaurants, these can be hotels, or these can be theaters, or some these kind like anything, museums, any businesses. So, for example, if you are aware of Yelp and what other are Airbnb, and so these are some uh, like. These are some of the examples of like what a proximity service is. This is actually something that is used to find the nearby places within a radius. So if you look at this screenshot, then you can see that I think this is from Yelp, and this is like this is the location, and near this location, these are some of the restaurants that are being shown on this. This is the Yelp, yeah. So these are some of the locations, nearby restaurants that are being shown within this location on this service. Now the thing is like we have to first understand the problem and discuss the design scope. So first thing that we can look at is like, can the user specify the search radius? For now, we can assume that we are just to keep the design simple. We assume that right now we do not give give this capability to the user to select the search radius. But the thing is that we only care about businesses within a specific radius, a fixed radius. Next thing is like, what is the maximal radius allowed? We can assume that it can be 20 kilometers, like more, not more than that, but within 20 kilometers, we want to find all of the businesses. Uh, Next thing is, can the user change the search radius on the UI? Um, like we can add this functionality. Maybe we cannot add like the user can enter the radius by like a dynamic radius by himself, but at least they have some options to select from. Maybe they can select from 0.5 kilometers, 1 kilometers, 2 kilometers, 5 kilometers, and 20 kilometers. So we just give them these five options to select from. Next thing is that because we need to have an option to add the businesses, delete the businesses, or update the businesses, because we can have like multiple we like because businesses open or close sometimes, and there are new businesses that are there, and there are a lot of changes in the businesses. So maybe some businesses open a new branch in some other area, and then they want to add that. So these kind of things, these needs to be added to your service. So we need to add that capability to be able to add the businesses, so that businesses can register themselves on this proximity service. Next thing is uh, the next thing is that, do we care about like because like if I am, for example, searching on Yelp, and let's suppose while searching I am maybe walking to the maybe walking nearby places, so will it change? Because when I am walking, then definitely the radius is changing, the distance to the places is changing, like radius is changing, or my actual latitude longitude is being changed. So based on this too, I want to update the nearby locations as well. That is something we probably don't want to do, because that will be very complex. We can assume that the walking speed of the user is very slow, so we don't probably want to do that. But one thing that we could have that we could do is that maybe when the user is driving, and maybe he opened the Yelp. The Yelp app was opened on his mobile device or any other device, and then the user drove to some different location. Maybe in that case we can update it. Maybe yeah. So, but the thing is that we do not want it to be real time, because that is not necessary, and that is going to make our system very complex. So we do not want to constantly refresh the page. Next thing is the functional requirements. So we want to return all of the businesses based on a user's location, and user location is based on the language, latitude and longitude pair and the radius. And like this next thing that we want is that business owners can add, delete, or update the business. And definitely this doesn't need to be reflected in real time, because if you are adding a business if you're adding a business in uh, if a business is being a new business is added on the service or Yelp app, then it doesn't need to be reflected immediately, because the thing is that we do not worry about the real time updates. It's not critical that something needs to be available immediately. So business can be, once it is being updated properly in all of the databases, then it can be shown at that time. So next thing is that the customers can view detailed information about a business. So when you are when customers are seeing this, when customers are seeing these like businesses on the page, then they can click on that specific thing. For example, they can click Manila Bowl restaurant on the page, and then they can view all of the detailed information of that business. So that is another feature that we want in our app. So this is another functional requirement. So these are some of the functional requirements that we want. Next thing is the non-functional requirements. Definitely first thing that we want is the low latency. So we do not want, whenever user is searching for something, this needs to be visible as quickly as possible so that they can view the businesses quickly. Because if something is going to take a lot of time to load, then users will get frustrated, and this will impact the user experience. Next thing is the data privacy. So location information is definitely sensitive data. So we do not want to have this location being compromised, because if some user is in a specific location, definitely this can be, and this can, if some attacker might be able to access your location, they can definitely reach you out. So this is very sensitive. You do not want the user's location to be compromised. So that's why we need to be able to, our app should be reliable enough to like secure the location of the users, so that it is not easily compromised. Another thing is that definitely we need to comply with these data privacy laws as well, because if you do not comply with laws and your app or your system is like has vulnerabilities, then you are being charged a lot of, or you can, these can be like, these things can be used against you, like you are not protecting the user's data. And like this is something that might come in crime as well. So definitely that's why we need to make sure that our system has data privacy controls. Last thing is the high availability and scalability. So we want to make sure that our system can handle large traffic spikes, and it can also like it is scalable. Like if more traffic is added, it should be scalable, and it shouldn't impact the availability of the system. It should be available most of the time. Next thing is the back of the envelope estimation. So before we dive into the high level design and discuss what components we need to use, we need to just like estimate like how much storage we might need for our system, or how many queries we will have to address per second. So let's assume that we have 10 million daily active users and 200 million businesses on our app. So based on that, we can assume that there are 5 search queries that are being made by per user. So if you have 100 million daily active users and each user is making on average 5 search queries, then per second load of the query will be 5,000, like 100 million times 5. We will divide it by 10 raised to the power 5. Why we divided it by 10 raised to the power 5? It's because we are converting the day into, we were assuming that we have daily active users, and we were converting it to million. and we were also discussing per day queries. So when we need to convert this to queries per second, then we need to uh, divide it by the number of seconds in whole day. Okay, next thing is the high level design. So in this section, we will discuss like the API design, because that is the most important one, the level design, the data model in our database, and algorithms that we need to use to find the nearby services. These can be related to some geo like geo services kind of algorithms. The first thing is that we want to discuss the API design. So, we use the RESTful APIs for this. So first thing that we wanted in our functional requirements is that we wanted to have uh, search nearby. Like we wanted to have the functionality to be able to search for the nearby locations. So whenever user is on the app and it selects a specific radius within its location, then we need to search for the businesses in that location, and then render those on the user's mobile device. So for that, we have this endpoint, which will be a get endpoint, and so let's suppose it's like called nearby. So this endpoint will return the businesses on maybe certain criteria, maybe based on the radius, and maybe based on the rating within, like it can maybe order the businesses based on the rating as well, and popularity as well. So the thing is that we will have three fields the in the request body, which is the latitude, longitude of the customer user's location, and radius is like within how much this meters we need to find the nearby businesses. Answer, like the response that we can get is probably maybe we can add the pagination as well in this, like pagination in a sense like on the first page you are getting like 10 results, and then if you click next, then you get next 10 results, then you click next, you get next 10 results, and so on. But the thing is that on one page you get 10 results, and those are the businesses, and you get the list of businesses. So these business object will have all of the details of the business. So this can be like, because we are seeing on this page this list. So you can see that here we have this business object which has the name of the business, the total rating or stars, the location, like how near it is, the like maybe review and those kind of things. So this is all that will be returned in the business object, and we will get a list of these objects in the API response. Next thing is next thing is like we also want to have the APIs for the business, because we know that in our functional requirements we want the business owners to be able to add the business, remove a business, or update a business. So for that we have these APIs. One first is the to get a business, which will return the detailed information. This is something that is based on the customer side or user side. So if user clicks this specific business, then they should be able to land to a new page where they can see all of the information about the business. For example, it's a restaurant, then maybe they can see the ratings, all of the reviews, and menu, pricing, all those kind of things. So this is the API to get the business details. Then we want to have the ability to add a business. So for that we have this post API. To update a business, we have the put API. To delete a business, we have the delete endpoint. And so this is what we want to have in our APIs. Once we are done with the APIs, then we can move to the data model. So in this, we'll discuss the read-write ratio. We know that this system, like proximity service system, has very high read ratio compared to, like it has very high read ratio compared to the write ratio. Why? Because it's not frequent that businesses are being added every single day, or these are being updated frequently. It's possible that a business is added in a few businesses are being added in 1 month and these kind of things. So right ratio is quite small compared to the read ratio, because read ratio is very high here, because a lot of we have just discussed, like we have 100 million daily active users and they are making 5 searches per day. So we have 500 million reads requests and per day. So which means that, and we saw that in the back of the envelope estimation, like we have 5,000 queries per second. So reads are like 5,000 QPS and queries per second, and write ratio might be like 1 or maybe even less than that in 1 second. So you can see that the read ratio is much bigger for the proximity services compared to the write ratio. So based on this, we need to decide our data schema and which database we want to use. So, so the like maybe for read heavy system we can use the relational database, for example, MySQL, and uh, so we can have like the database tables that we want in our services. Like we want to have a business table, right? Uh, because this will be providing us the list, or because we will return the list of tables within that radius. And we also want to have the geospatial index table. We will discuss like what is this. Will be helpful in finding the this will be helpful in indexing your like longitudes and latitudes, and based on this you can return the results in uh, faster with low latency. So the business table will have all of the information about a business, for example, business ID, address, city, and this is just a few examples, few columns, but definitely it can have a lot of other things, reviews, comments, and menus, and a lot of things. If you're talking about menus, then maybe it is being the type of the business, all those kind of things can be there. And next thing is the GeoIndex table. So GeoIndex table will be used for efficient processing of spatial operations. So with this, you will have to, like, we need to be able to find the businesses with high performance. And because the thing is that the business table can be really big, because if we are talking about a global Yelp app, then definitely business table can become really big, because there are a lot of businesses that are being in the like worldwide. Yes, Arslan.
मैम अगर हम इस पे इंडेक्स कर लें
Hmm.
लेटीट्यूड लॉन्गिट्यूड पे सेम टेबल के अंदर,
Hmm.
तो वो कैसे डिफरेंट होगा सेपरेट टेबल बनाने से? उसमें ज्यादा एफिशिएंट नहीं होगा?
अच्छा, लैटिट्यूड लॉन्गिट्यूड वाला तो हम इंडेक्सिंग करते देंगे, बट वी विल डिस्कस लाइक दिस इज नॉट दैट एफिशिएंट. बट व्हाट वाज एग्जैक्टली योर क्वेश्चन, लाइक ये.
मैम जियो इंडेक्स के लिए उसने सेपरेट टेबल बनाया ना,
Hmm.
तो मैं एक पूछ रहा हूँ कि अगर सेपरेट टेबल की बजाय बिजनेस टेबल के अंदर ही हम इंडेक्सिंग कर लें लैटिट्यूड लॉन्गिट्यूड, वहां पे भी तो है ना?
That is one thing. So we can do that definitely, but the thing is that because latitude, longitude, it can be really big. You know, because the thing is the table is very big. अगर आपके ना, if you because latitude, longitude is different for every single business, right? So which means that usually indexing helps with some values that are not too much, like that are maybe kind of, if you have if you know about clustering or those kind of things, then you know that indexing works best on like on the on like columns that do not have like very unique values, right? So in this case, latitude, longitude is, you know, kind of unique for every business. So I think that will cause this indexing to not work much efficiently. So for that purpose, we use the geoindex table. We'll discuss that what exactly this geoindex table will store, and how it will help improve the efficiency in getting the nearby businesses. Okay, so let's look at the high level design. So, like we want to have our system, like we know that our system has two parts. One is to search for the nearby locations, and other is to have the capability to add, remove, or delete businesses. So we want to have two services. One is the location based service, which will be used to um, select the nearby businesses, search for the nearby businesses, and then another is the business service, which will be just to add, delete, update businesses. Definitely these can be implemented in different servers, and maybe these can be microservices. Then these can be scaled horizontally. These are independent of each other, so we do not need to worry about. Um, so next thing is like we know that the write ratio is kind of small, so we can have a primary database for that purpose. And because writes are small, so we can just directly write to this primary database, which is just used for writing. And then we can have separate replicas for read, because the thing is that read ratio is very high. If we will use the same database for reads, then we are just causing performance bottlenecks. So when the writes will become slow, reads will become slow. So this will cause some problem for us. So what we can do is that, since our system is read heavy, so we can use one primary database for the write operations, because write operations are not that much, and we can use multiple replicas for read operations. So we using these multiple replicas will help us in distributing the traffic evenly among the servers. So if this server is already filled up with many requests, then we can redirect the traffic to this replica and so on. So what we do is that whenever a business is added, removed, or updated, whenever write operation is being performed on the primary database, the like those changes are being replicated to all of the replicas. Like we just replicate these to all of the replicas, and we can have the eventual consistency. Here we do not need to worry about strong consistency. So even if a business after replication, if a business is being updated here but it's still being in process for this and this, and if a user if one user, so one user might be seeing the updated business on their app, other might not be able to see because the replication has not been completed yet. So we do not need to worry about, like, because strong consistency is usually when you want every user to see the latest information. Eventual consistency is like when eventually it can reach to all of the users. So we do not need to worry about strong consistency here, because this information is not critical. Strong consistency is usually required in banking applications, where every user must be able to see the updated balance at the same, like no one should see, like different users shouldn't see different data. So uh, so next thing is the load. Like we have this load balancer as well. So this load balancer will definitely is just something that can help in scaling, because we have scalability and high availability requirements. So we can use the load balancer to distribute the traffic, because we know that this will be a lot. This will require a lot of traffic. This will probably not require too much traffic. So here, scaling will not require that much scaling. Will definitely for a load location-based services, we will need to add and update more servers based on the add or remove server based on the traffic. Um, okay, next thing is and we also know that these services are stateless, because it is not one business is independent of the other business and those kind of things. Services, location-based services independent of the business service, so we can easily make this scalable. And yeah. Next thing is to we need to discuss the algorithms to fetch the nearby businesses. So for these kind of things, like usually like Yelp or any other proximity services, they are not usually using MySQL or relational databases. They are probably using the geospatial databases for these kind of information, like to store longitudes, to latitudes, longitudes, and to get the nearby locations based on those. So usually we use the geospatial databases for these kind of things. And um, so the thing is that we can have, like, what we can do is, like, we have multiple options. So to for these geospatial databases, we can probably discuss these and discuss the trade-offs, like which one will be the better one for our case. So what we can do is, like, first thing that we can do is, like, we can do the two-dimensional search. So this is probably the most naive way to do this. So what we can do is like we can define a predefined radius using something like this circle, and then we can say like find all of the businesses within this radius. So maybe this is my location, and I am on the center of the circle. So within this radius, I want to find all of the businesses. So this will return me this. Like I will get 5 nearby businesses within my radius, and if something is that is outside my radius, I will not get that. So what we can do, we need to do two-dimensional search here. Why? Because we are using x and y values maybe in terms of longitude and latitude. So so this is my longitude and latitude, and then I will be saying, okay, based on the radius, uh, something that is within longitude or latitude of some business that is within radius minus my longitude, or radius plus my longitude, or radius minus my latitude, or radius plus my longitude, something like that. Within this, if business is within this range, I'm going to return those. But the thing is that to get all of those, to get this, we can just have this simple SQL query. We can say, okay, select the business ID, longitude, latitude from the business table, where my latitude is between the my latitude minus radius and my latitude plus radius, and longitude is between this. Like these are the ranges that are where my latitude or longitude should be. But the thing is that this query is highly inefficient because we will have to scan the whole table. First thing, if we are not adding indexes, then we'll have to scan the whole table, and the businesses table can be really, really big. Second thing is like if we add indexes on longitude and latitude columns, we want to see if this will improve the efficiency. It will not improve the efficiency because the things that you have two-dimensional data. So you are getting the longitudes and like latitudes, right? So this can definitely reduce your search scan on the table. So you can probably say, okay, these many rows for the longitude, these many rows on the latitude, and then once you have got this, then you will have to perform the intersection on that. You can see that you are still returning these data sets with smaller, like instead of returning this whole longitude or this whole latitude, you are saying, okay, these many rows for the longitude, these many for the latitude, and then perform the intersection. So these data sets are still big, and the intersection will be inefficient. So uh, the thing is that this two-dimensional search is not that efficient for our use case. So because each data set still contains a lot of data even if we add indexes. So and the other thing is that the indexing can improve your search speed in one dimensional only, and when you have multiple dimensions, then uh, maybe you can think about mapping your two-dimensional data to one dimension to improve your search speed. So what we can do here is like we can look at different indexing methods that can help us to like map our two-dimensional data into one dimension. So there are two kind of algorithms that are used in industry. One is the hash algorithms, and other is the tree algorithms. So hash algorithm example are Evangrid, GeoHash. We do not need to just go into or learn like what are these or how these work, but we can just look at quickly like what is quad tree and those things. So the thing is that what these implementations usually do is that, like, definitely their implementation details might be different, but the goal is kind of same. Is to divide the map into smaller areas and build indexes on those smaller areas for fast search. We will just look at how can we divide the map into smaller areas. So let's look at this one. So we can use what we can do is maybe we can do evenly divided grid. So what we can do here is that we can divide the whole world into small grids. So if you look at this, so this is the map of our world, and these are small grids that we have divided it into. But the problem with this approach is that like some of the areas or some of the cities, for example, New York downtown, will may have a lot of businesses, right? But other areas might have no businesses at all. So this will cause very uneven distribution. So maybe in this grid, I am getting a lot of businesses. In here, I am getting nothing. So this will cause uneven distributions. This is not a good approach for our, like, this is one of this is the trade-off for evenly divided grid approach. We look at the trade-off for the two-dimensional search. We also looked at the trade-off for evenly divided grid. And so next thing that we can try is maybe we can try the geohash. So this is much better than evenly divided grid option, because what you do in this case is instead of dividing the whole world into smaller grids and use those specific grids just for radiuses, what we can do is we can, for example, have this radius, really big radius. And if this radius has a lot of businesses, then what we can try to do, for example, if you only want to return 100 businesses within a radius, and let's suppose within this radius we have maybe 2000 businesses. So that is too much. We do not want to return that much. What we can do in that case is we can, so this is in this radius, we have this grid. So what we can do is we can divide this grid smaller, uh, smaller subgrids. So initially we can divide this into 4 quads with these binary representation. First quad with 0, 0, then 0, 1, 1, 0, and 1, 1. So these are the latitudes, longitudes that we have. So we can say that something that is like in this quadrant, like this is first quadrant, second, third, fourth quadrant. So we say that we just divide it into 4 quadrants, and then we can further subdivide this into so when we divide it, so let's suppose we are here now we can divide this further into 4 quadrants. So we can divide it like this, then we can again divide this quadrant into like this 4 quadrants. We can again divide it into 4 quadrants like this, and so on. We can do this until we are able to reach our goal. So and how we can divide is like once we have divided, like this was the first division that we did. And next what we can do is like we can say that so we are saying that the latitude range that is between -90 to 0 is represented by uh, first quadrant. Latitude range between 0 to 90 is represented by 1, and so on. So now what we do is like what we so the thing is like let's just look at here again. So we are representing it with 2 types of data, like latitude and longitude. So here we are saying that latitude range -90 to 0 is represented by 0, and longitude range between minus and latitude range between 0 to 90 is what was right here. Okay, right. So here latitude range between 0 to 90 will be represented by 0, and latitude range between like -90 to 0 will be represented by this thing. So next thing we can do is like so we have this latitude range, and then we can say that longitude range between this is represented by 0 and 1. Now that we have these 4 quadrants, next we can further subdivide into, then we can further subdivide this into these 4 quadrants. So okay, so then what we can do is like we can divide it into further 4 quadrants, right? So here, like we have this first quadrant, and we want to divide this into further 4 quadrants. So what we can do is like we can say, okay, um, like into to convert to distribute into 4 quadrants, keep this first one as it is, and then to convert it again, we use again these 0, 0, 1, 0. 1 1 and 0 1. So you can see that again we have 0 0 1 0 1 1 and 0 1. Similarly, if we are dividing this quadrant, which is this one, then we keep this 1 1 at the start and then we represent the remaining 4 with this one. So if we have to further divide, let's suppose this quadrant into further 4 divisions. So what we can do is like we have something like 0 1 0 1. 0 1 0 1 will be at the start and then we can use these 4 things again. Like first one is the 0 0, second one will be 1 0. Initially we'll still have 0 1 0 1, and third one will be 0 1 0 1 and 1 1, and fourth one will be 0 1 0 1 0 1 and 0 1. So we can continuously divide it into smaller subgrids. And the thing is that we want to see like when we need to stop. Definitely we cannot divide it indefinitely. So one example of this is like yes, Wahab.
मैम ये जो लिखा हुआ है जी बाइनरी है या इसने जस्ट लॉन्गिट्यूड या लैटिट्यूड को प्रेजेंट किया हुआ है क्वाड्रेंट की बेस पे?
Yeah, it's just kind of you maybe it's not binary. Maybe you can represent this with binary, but this is something that is there to like represent your longitude and latitude. Like 0 is telling, like we discussed here, like 0 is telling like that longitude ranges between 0 to 90, right? And 1 is representing that latitude range is between 0 to 90, longitude range between -180 to 0 is represented by 0 and like this.
ओके, क्योंकि ये जो फर्स्ट वाला है वो कुछ इस तरह 0 1 2 3 बन रहा है, लेकिन
Hmm.
ठीक है।
As one example of like geohash, so this is something that is called geohash, and then we can store that. Now you can see that this has been converted into one dimension, right? And this can be stored in one column. We have converted we are representing, like we are using these 1 zeros to represent longitudes, latitudes ranges, and then these can be stored in one column. So we have like converted our two-dimensional data into one-dimensional data, and then we can perform indexing on that one. So this can be stored now in geohash table. That's why we needed geohash table for indexing. Okay, so you can see that we can also like we can also like instead of storing this as a string, definitely the string will become really big if your subgrids are very if you have a lot of like subgrids. So instead of doing that, you can definitely just use this as a binary, and in binary this can be represented as this, which can be stored in your geohash table. And one more thing is, like if you look at an example of geohash for Google headquarter, with length is equals to 6. I think by length 6 here mean is that your like is your that your geohash is like your one subgrid is divided into six subgrids. Like you have divided it at 6 levels. So here we were seeing that this was 2 levels, right? So this was 2 levels, and if we further divide it into 4 parts, then this will be at third level. Then we further divide it into 4 parts, this will be at fourth level, and so on. So this is an example of 6 levels geohash. Um, so the thing is that it has like geohash has 12 precisions. Like we also discussed that these are called levels, and like we are only interested in geohash's length between 4 and 6, because the thing is that if you increase your length of the geohash, then this can make your radius very small, and you will just the distance will become smaller and smaller if you will increase your geohash, and distance will be larger if you reduce your like if you keep your geohash smaller, like smaller, and if it is larger, then distance will be smaller. So we want something that is reasonable. So if you look at this table, then you can see that if you have geohash length of only 1, then it's kind of really big distance, and if you have a geohash of 12, then it goes into centimeters. So this is something this range is something that is reasonable for us. That's why we are interested in the geohashes between 4 and 6. Next thing is and the thing is that how exactly do we want to find the right precision? Like how do we know that which length of geohash we need to look into this? So maybe we want to actually find the minimum geohash length within the user-defined radius. So if you look at the geohash length example, then we can, like if user has selected a 0.5 kilometer radius, because we discussed this previously that we want to provide this capability to user to select these different kind of different 5 options of the radius from the maybe from Dropdown or something else. So if user selects 0.5 kilometers, then we can use geohash length of 6. If it selects 1 kilometers, then definitely we can reduce it to span more area. With 20 kilometers, we can use 4 to span more area and those kind of things. So we can use these precisions to select based on the user selection that which geohash length we need to use for our use case. I think we can just end the discussion for now, because there are a lot of other things that we need to discuss, and we cannot discuss this in today's session. We can discuss this tomorrow. If you have any questions, then feel free to ask. Okay, I think if no more questions, then we can end the session.